Thank you everyone for coming today. Before we begin, I just wanted to say a very quick thank you to Ricky from the Math House, wherever Ricky is in the back, and also to Ronaldo from ITS for helping out. Just wanted to thank them for everything going smoothly today. It's with great pleasure that I get to introduce the speaker today, Dr. Pam Warton. I don't know if you knew this, but she has 2 bachelor's degrees, one in mathematics and one in computer science, both from BGSU. She started her career at General Motors, working in finite element methods after she graduated. She was working in Detroit, and while there at General Motors, she was put in charge of training new programmers. And it was that training that actually caused her to realize how much she loved teaching. And having that realization, she went and pursued her PhD at BGSU and her PhD in mathematics. After receiving that PhD, she taught at BGSU, Siena Heights, and then we were extremely fortunate in the year 2006, she came to the University of Finley. She was instrumental in actually helped create the Euler Math Club here at UF. She also was the founder of the Tau section of Pi Mu Epsilon. She brought that here to UF as well. And if you didn't know, she's been awarded the University of Finley's David L. Allen Teaching and Excellence Award, and also the Mathematical Association of America's Distinguished University Teacher Award. So with great pleasure, I get to welcome Dr. Pam Warton.
Thank you.
Lots of good things in there.
Lots of yummy stuff in there. Okay. First of all, give me a minute because I got to talking, and those of you who know I like to talk. And I forgot to put my mic on, so hang on a sec. Okay, hang on. Yep, this is going well. If somebody applauds, I'm going to come out there and smack you. Okay, how's that? Can you hear me? I'm not looking over there. Can you hear me? Okay. All right. Well, welcome. Like he said, I don't think he said, I retired last year, okay? So I've been sitting around the house doing home improvement, which has been kind of fun. And when they asked me to come and speak, I thought, well, what is it I love to do more than anything? And the answer is gaming, okay? I am the original gamer. I am 60 years old, and I started playing Pong when I was 8 on the television. It was the neatest thing I'd ever seen. I can't tell you how much money I have spent in the old arcades where you actually had to put quarters in, okay? So I've been fascinated with games since I was little, so it made sense to apply the other thing that I love, which is mathematics, to games, okay? And that involves 2 areas, logic and strategy, okay? This morning I talked a little bit about some logical ways to win games. Today, this afternoon, I'm going to talk about strategies, okay? And I'm going to put a plug in for all the math professors here. We math professors, there's one thing we hear probably more than anything from our students, and it's, why do we have to learn this? Right? How many times am I going to do algebra in my life? I found a quote, and I wanted to start my talk off with this quote. Oliver Wendell Holmes, people's minds, once stretched by a new idea, never regains its original dimensions. And this is how I live my life. I never stop learning. I'm taking an astronomy class now from Stanford University online. Always keep learning. And that's what I want to do today. I want to stretch your mind a little bit, okay? Okay, so we are going to talk about the strategic part of game theory. This is the mathematical study of making decisions, okay? It started in mathematical economics. Has anybody seen the movie Beautiful Mind? Have you seen that movie? Yeah. It's about John Nash, and his work is really what got this, subset of mathematics going. And it really took off when he came up with the Nash equilibrium. Okay, so we're going to talk about what all these things mean. Where is it used? Okay, game theory is used everywhere. Everything can be looked at as a game, right? When should you ask for a raise? Bidding at an auction, two people bidding against each other. Any sort of negotiations, like company with a union or any sort of contract negotiations. What should you price your product at? When should you release your new product? The stock market, holy moly. Is that a game? Absolutely. Politics, ick, but it's a game. Dating. You guys are dating age. You know that's a game. Right? And it even goes so far in biology, evolution, predator-prey models, gambling, sports, war. There are two branches of strategic game theory. One's cooperative, when people are working together towards a common goal, and the other is non-cooperative. We're going to be focusing on the non-cooperative branch today. Okay. Here is our formal definition. The only thing I'm going to, you all can read, branch of mathematics concerned with the analysis of strategies. Okay, so that's what we are going to be looking at. There are three parts to analyzing different games. You have your players, that's the entities that are, involved in the game. They're assumed to be rational. Not always a great assumption, but it's something that we are going to assume. Set of strategies, a complete set of possible actions. We can't ignore anything, okay? And the payoff or utilities, it's some sort of numeric measure of the benefit to the players, okay? The highest payout should be to the best outcome. Three things, okay. Now, nothing makes sense without an example, right? So, I should have lined up my volunteers before, but again, I got to talking. Ladies, would one of you like to come up? Okay. Thank you very much. What's your name? Lindsay. Lindsay? Yeah. Lindsay, come on up. I'm going to put you over here. And I need somebody that doesn't know Lindsay. You only know those two people. Okay. You were up this morning. I want somebody... Ladies? Yeah, you. One of you want to come up? How about blue sweatshirt? What's your name? Sydney? Sydney. Okay. I'm going to put you over here. Okay, now we are going to, this could totally backfire on me. Okay, so just beware. Okay. We are going to do the most famous example in game theory called the prisoner's dilemma. Has anyone ever heard of it? The prisoner's dilemma. You've heard of it. Okay, all right. So, you guys got together. You don't know each other. You're not really friends, but you're going to rob an electronics store. Okay? Yeah, okay. Someone called the police and tipped them off, okay? And they found you both skulking around in the back of the electronics store, okay? You're both arrested for trespassing, okay? You're put into separate interrogation rooms, okay? You're told the following, okay? I need you to really pay attention to this, okay? Okay. We are currently charging you with trespassing, which has a mandatory 1-month jail sentence, okay? You're going to jail for a month, at least, okay? We know you were planning on robbing the store, but we can't prove it. So we need your testimony against the other one to provide proof that you were planning on robbing the store. In exchange for your testimony, we will dismiss your charge, okay? You go completely free, but your partner is charged with attempted robbery, which is a 12-month jail sentence. Make sense? Make sense? Okay. All right. We are offering your partner the same deal. You're both getting the same deal, okay? If both of you confess, your testimony is not as valuable, and your jail sentence, instead of being 12 months, will be reduced to 8 months. Does that make sense? Yeah. Okay. Now, what do you do? Okay. So, everything is confidential. Here's a piece of paper. Nope, not yet. You can't. You're in separate interrogation rooms. This is one of the strategies of police, right? To keep you guys separated. These monsters are the only pens I have. Okay. All right. So you're going to write a C for confess. Okay. Get you off. Your partner goes to jail for 12 months. Or you're going to put a Q for you're going to stay quiet. Those are your two choices, okay? I hope this works. It didn't. Okay, thank you. Thank you. Let's hear it for our volunteers. Yes. Well, this backfired. I picked two very lovely, kind young ladies. Okay. Can you see what they wrote? They both put quiet. Okay. Okay. This is actually unusual. It's been found that the only people who say quiet are people who have the community as a whole in their best interests. People that have their own personal interest in their mind typically say confess. Do you see what I'm saying? Okay. Okay. What would the rest of you do? Okay. Just out of curiosity, how many would have confessed? How many would have kept quiet to see if people just aren't playing? Okay, there were more confesses than quiets, okay? And that is typically what happens, okay? All right. Okay, so would you do something different? Okay, now we're going to analyze this. We're going to analyze this. Who are our players? Player 1, player 2, okay? What are our strategies? Quiet or confess, right? Payoff or utility, some sort of numeric measure of the benefit. This is going to be the jail time, okay? Since the highest number has to be with the best outcome, we have to use negative numbers, right? So my payouts are 0, -1 for 1 month in jail, -8 for 8 months in jail, -12 for 12 months in jail. Yeah? Okay? Okay. We are going to create the strategic form of this game. Okay? All right, so I'm going to put player 1 over here with the rows. I'm going to put player 2 with the columns. What are player 1's possible strategies? Quiet and confess. What are player 2's possible strategies? Quiet and confess. Yes? Okay. Now, let's fill in the first box. If they are both quiet, what's going to happen? They both get 1 month in jail. Yes? The first number goes with player 1, second number goes with player 2. Okay? What if player 1 confesses and player 2 is quiet? Player 1 goes scot-free. Player 2 gets 12 months in jail. Yeah? Okay. If player 1 is quiet and player 2 confesses, they swap. And if they both confess, they get each 8 months in jail. Okay. So this is a way to, in a table form, to view our information. Okay? Now, I'm not going to show you yet how this happens, but game theory says that what will happen most often is that both players will choose to confess. Okay? So, eventually we're going to call that the Nash equilibrium, but negative 8 is the thing that happens most often. And this has caused a lot of arguments. Why? Because isn't -1 a better outcome than -8? It is, but it's not what happens. This is a paradox that game theory points out. It's the difference between an individual having the entire society well-being in view or a pursuit of personal gain. Okay, depends on what happens. This happens many times when there is a single interaction between strangers, right? Why? Normally, you could care less if she goes to jail for 12 months. You get to go free. Well, see, that's not the kind of person you are, though, so, which is why my example didn't work. Okay. Okay. I found this quote from Psychology Today, okay? And I just want to read it with you because does the world ever get you down? How mean and nasty people are to each other? You guys are like social media. People are mean. They are. Interacting with strangers, which is now commonplace in so much of the human experience, can be thought of as playing one-off prisoner's dilemma. Modern conditions, we constantly find ourselves in situations that tend to inherently breed selfishness. Want to understand why there's so much nastiness in the world today? Maybe the problem lies in the fact that so many human social interactions are between strangers who have no expectation of interacting with one another again. Okay? But the point is, even though it didn't work in my example, and I knew that was a possibility, game theory has been accurately used to model human behavior. Okay? Okay, now, I want to talk about how we get to the conclusion that -8 is what's going to happen most often. That's going to involve computing the Nash equilibrium. Here's the beautiful mind. He was mentally ill, if you've seen the movie. I don't know. It seems so often mathematicians in movies are mentally ill or evil. I don't know why. I don't know why that is. Although Hidden Figures, everybody go watch Hidden Figures. One of the best math movies out there. So this chronicles the discovery of the Nash equilibrium. A Nash equilibrium is the strategy that maximizes a player's payoff given the strategies used by other players. The strategy confess is our Nash equilibrium in the prisoner's dilemma. Okay? Assumptions, both players are rational. Each player's belief about strategies are true. We're not having any conspiracy theories, that sort of thing. Okay. So, how to find the Nash equilibrium? We want to find a dominant strategy. Okay? How do we do that? We are going to consider player 1's best reply to player 2's strategies. Okay? Let's suppose player 2 decides to be quiet. Okay? I am going to look at the numbers -1 and 0. Yes? That's player 1's reply to that strategy. Which one of those numbers is higher? 0. Yeah? I'll put a green box around it. Player 2 could also confess. What is player 1's best reply? I'm comparing the numbers -12 and -8. Which number is bigger? -8. I'm going to put a green box around it. All right? Now, I'm going to leave the green boxes, and I'm going to consider player 2's best reply to player 1's strategy. So player 1, let's say they pretend they are going to be quiet. I'm going to compare the numbers -1 and 0. 0 is the largest number, so I'm going to put a blue box around that. If player 1 confesses, I'm comparing the numbers -12 and -8. I'm going to put a blue box around the bigger number. Looky there. There is one box that has both of the numbers boxed. That is our Nash equilibrium. Okay, does that make sense? Okay. So, -8 is our Nash equilibrium, and that's how we are going to find them. These are called pure strategies. Okay? Each person should always confess. Okay? Now, we had a cute little 2x2 table, right? What if we had 3 players and 3 strategies? Eek. Now I'm looking at a 3x3x3 cube, right? I'm going to look at P1's replies if I fix P2 and P3's strategies. Do you see how that's okay? All right. What if I have more players? Have you ever heard of a hypercube? 4-dimensional cube? Yeah, no, it's math geeks. We like that kind of stuff. Okay, all right. So it gets very complicated very quickly. Okay. What if there is no pure strategy that you should always use? What are we going to do? Well, Nash also came up with Nash's theorem. Every finite game has a Nash equilibrium. So there's got to be one, even if there's no pure strategy that you should always pick. All right. Now we have to introduce a little probability. Yay. Have we all, or are we all in like Math 123 or 221, or have we all had some statistics? I'm seeing, okay. Okay, so the Nash equilibrium can be something like, well, you should be quiet 10% of the time and confess 90% of the time. That's a mixed strategy, okay? Okay, new scenario. Drug dealer sets up on the streets or at a park. I don't know why I picked such doom and gloom examples. I now apologize for that. Okay. With no police presence, they anticipate they will make 100 drug sales. Okay. Yay, drug dealer, I guess. Okay. The police want to disrupt the drug trade. Okay. Their payoff is going to be the number of trades they stop. That makes sense, yeah? If they both end up in the park, only 40 trades occur. If they both end up in the streets, only 20 trades occur, right? Does that make sense? It does. And if you're going to buy drugs and you see a police car driving around, you might wait, okay? If the dealer is on the streets and the police are in the park, 90 trades occur. Why? Well, the police still have a presence. But if the dealer is in the park and the police are on the streets, the dealer is completely insulated, right? So he's going to make all 100 trades. All right. Now, let's look at our strategic form. Police with the rows, dealer with the columns. The police can patrol either the street or the park. The dealer can set up in the street or in the park. If they're both in the street, only 20 trades will take place. That means the police disrupted 80 trades. Yeah? Okay. If the police are in the park and the dealer is on the street, there is still a police presence. The police have to go in and out of the park, right? So there's 90 drug trades and 10 are disrupted. If the police are in the street, the dealer's in the park, all 100 trades occur, okay? And if the police are in the park and the dealer's in the park, 40 trades occur and 60 are disrupted. So this is our strategic form, okay? Is there a pure strategy? Well, let's do what we just did with the prisoner's dilemma. If I look at, okay, I didn't make it nice like I made the other one. Say the dealer is on the street. The dealer is on the street. What two numbers am I comparing? 80, and I'm checking to see if you're with me, and 10. The bigger number is 80, yes? Okay, if the dealer's in the park, what numbers am I comparing? 0 and 60. So the 60 is the higher number. Now, let's switch. Police are on the street. What number am I comparing? 20 and 100. So 100's the bigger number. In the park, if the police are in the park, I'm comparing the numbers 90 and 40. 90 is the bigger number. Okay. This doesn't look quite as pretty as the prisoner's dilemma, does it? There is no one box that has both things circled. There is no pure strategy for this situation, okay? So that means, but we know there is one. We know there is one. So how do we find it? It's going to be a mixed strategy. And here comes some math. Yay. Okay. Let P be the probability that police are on the streets. D is the probability that the dealer's on the streets. Okay? I've only got two options. So the probability that the police patrol the park is 1 minus P, right? They have to add up to 1 or 100%? Okay. Okay. All right, let's recall some basic probability. Ooh, should I pick on somebody? Who's had 123? Oh, nobody's going to volunteer. Nick's had 123? Justin's, oh, okay. Probability of getting a pizza. This is a standard probability question. Probability of getting a pizza with pepperoni is 65%. Probability of getting a pizza with anchovies is 5%. What is the probability of getting a pizza with both pepperoni and anchovies? Justin. Dang it, I should have hidden that. Okay, We're going to use the multiplication rule of probability. If you have two independent events, you can just multiply the probabilities. Does that sound familiar, guys? Okay, all right. We're going to assume our events are independent. Okay. Okay, multiplication rule. So what do we have? Streets and streets. What's the probability? P times D. Yeah? Multiplication rule. Streets and park. P times 1 minus D. Multiplication rule. Park and streets. 1 minus P times D. And park and park. 1 minus P times 1 minus D. Multiplication rule all the way down. That was easy, yeah? Okay, now, this might be something that wasn't covered in 123. It's definitely covered in 221. It's definitely covered in, oh my God, I forgot the number. 410, thank you. Okay, expected value. Expected value is a different way to think about the mean, okay? So, completely different example. Weather calls for 20% chance of 1 inch of rain, 70% chance of 2 inches of rain, 10% chance of 3 inches of rain. How do we figure out how much rain we expect to have? Well, we take the probability, 0.20, times my data value, which is 1 inch. That's what I have right there. And then I add 0.70, my probability, times my data value, which is 2 inches of rain. And then I add my probability, 0.10, times my data value, which is 3. Add them up, I get 1.9 inches of rain. And that makes sense. Why? Why should it be less than 2? Why does that make sense? Well, there's a higher probability of a smaller amount of rain, right? So that would drag it a little bit less than 2, okay? Here's our mathematical formula for expected value, okay? So it's kind of like an average, okay. Here comes some math. Woot. Okay, all right, so what is the expected value for the police? Well, what did I say we did? We take the probability times my data value for the police. So that gives me P times D times 80, yeah? P plus, P, no punchline, wait, back. Okay. P times 1 minus D times 0. Plus, oh goodness, that resonated. 1 minus P times D times 10, plus 1 minus P times 1 minus D times 60. This is my expected value. Okay? Now, algebra, I'm going to spare you that. Okay? This all boils down to this lovely equation. Okay. And I'm going to give a little commercial for applied mathematics right now. If you see two quantities multiplied together, that typically means that there was some interaction between the two variables, okay? So when we see this P times D, that means there were police and dealer interactions. What did that do to the expected value of my police? It increased it, yes? And that makes sense. That makes sense. Okay. Now, we're going to do the exact same thing for the expected value of the dealer. Probability times payout, probability times payout, probability times payout, probability times payout. And we come up with this expected value for the dealer. If there are interactions between the police and the dealer, that is subtracting from the expected value of the drug dealers. Okay. Okay. I have two equations. Yeah? What are we going to do with them? All right. Well, we want to consider, remember back when we found the Nash equilibrium, we looked for the best reply to a pure strategy. Okay? So, excuse me, we let P be the probability that the police patrol the streets. So if I have a pure strategy, the police are always monitoring the streets, my P is going to be 1 or 100%. The pure strategy where the police patrols the park, that's going to be, my probability is 0 that they're going to be in the streets. Okay, that makes sense. That's exciting. Yes, it is. Why? Well, if I substitute P equals 1 into my expected value of the police, P equals 1, that's a minus 60, P equals 1, simplify, I get that the expected value of the police is 80D. Okay, that's not so exciting yet. Okay. If they patrol the park, P equals 0, I'm going to substitute that back in to my expected value, and I get this equation. What are those? Those are straight lines, right? What? Thank you, Adam, for showing amazement and shock. Okay. What do we like to do with straight lines? We like to graph them. Okay. Okay. So the red line goes with P equals 1. The blue line goes with P equals 0. Where do you suppose the Nash equilibrium is? Where they intersect, right there. Okay. How do we find out where two lines intersect? Okay, my hearing sucks, so it's not very good. How do we find out where two lines intersect? Set them equal to each other. So we set the two equations equal to each other. Okay, and blah, blah, blah. My D is 6/13, or about 46.15%. And if I follow this intersection point down, it does look like it's about at 0.46. Yeah? Okay, so we got a percentage. That was for streets, right? D goes with streets, P goes with streets. Okay, guess what we're going to do now? Same thing, different equations. We're going to repeat with the police. I'm going to look at their best response to pure strategies. So D equals 1, D equals 0. Okay? So I'm going to let D equal 1, plug that into my formula. I get that guy. D equals 0, plug into my formula. I get this guy. Straight lines again. Okay, so we're going to graph. Again, red goes with D equals 1, blue goes with D equals 0. They intersect. That's going to be my Nash equilibrium. Where is that at? Let's estimate. Oh gosh, it looks like it's about 38%-ish. Okay. Let's see, we're going to set those equations equal to each other. And that gets me 38.46%. Okay. Now, what is this telling me? I have a Nash equilibrium with mixed strategies. Police will patrol the streets 38.46% of the time, and they will patrol the parks 61.54% of the time. The dealers will be on the streets 46.15% of the time, and in the parks 53.83% of the time. If they both stick to that, they will get the best results that they possibly can, both of them. okay? Now, what else can we tell by these graphs? What's the chance that the drug dealers are going to analyze this with game theory? Okay. So the police will look. What is the percentage that the drug dealers are setting up in the, oh crap, I forgot. Okay, what if they are setting up less than 46.15% in the streets? Well, that means my D is on this side, right? So that means I want the expected value to be as high as possible. So I'm on this chunk of this line. This one went with P equals 0. So that would mean that the police, to combat that, would be in the streets to increase their expected value. If they are in the streets more than 46% of the time, I want the highest expected value, so I want something along this line. This went with P equals 1. So the police will then have a pure strategy of being in the streets. Okay. Do you kind of see how this is working? Okay. Okay. Okay, that's what I just said. Okay, so today is all about picking strategies. Picking strategies, okay? Strategic board games. I want to give you some suggestions of board games to try, okay? Like I said this morning, my son really likes really long board games, okay? The one we played was like 19 hours long. I just don't have that in me to play a game that's... It took us 4 hours just to learn the dang thing, okay? But obviously chess is good for strategies. Kill Dr. Lucky, one of my favorites. Has anybody played it? Oh my gosh, you guys. It is so much fun. Azul is a strategic game about color. And Pandemic, which is particularly appropriate, is a cooperative game to kill a disease, okay? And all of these will help your strategic thinking. Longer games, Catan, that's classic. Has anybody played Catan? Okay, quite a few people. Terraforming Mars? Yeah, oh, I got a game geek back there, yay. My current favorite is Arc Nova. Nobody's ever heard of it. But you've heard of it? Did you? Where is he? Do you like it? Oh my God, it is my favorite game right now. You get to build a zoo. And it is so much fun. And I know there's a lot of pre-vet people here building, so that's building a zoo. Okay. What are some games that will increase your strategic thinking with video games? Civilization. Everybody has had to, well, I shouldn't say that. Not everybody's into video games. Have you played Civilization? Yes, okay, okay. I actually have not played the Warhammer series, but it's supposed to be very strategic, and I think that's next on my list. Has anybody played it? Warhammer? Okay. Okay, games are a waste of time. Absolutely not. They can improve your problem-solving skills. They can improve your strategic thinking. Some of them, not all of them. How many of you play the phone games that are mind-numbing? Yeah, and sometimes you need that, right? It's a method to relax. It's a method to relax. But I don't think playing games is a waste of time. I think you can learn a lot from it. You want to know my deep, dark secret? Okay, so my first game system was an NES. Okay, I told you I'm an original gamer. All right. I worked at General Motors. I worked there for 5 years and never missed a day of work. This is how competitive I am. Okay. I got the game Wizards and Warriors for NES. I'm sure you've never heard of it. You have, okay. There's no save. There is no save on this game. I missed my first day of work in 5 years, actually 2 days, to finish playing Wizards and Warriors on the NES system. Okay, so I am fairly competitive, but I also have good logic and strategic skills. And how did I get those? I think by playing games. Okay. Thank you for coming. I hope you got something out of it other than extra credit. Does anybody have any questions? Yes. 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 Frankly, I don't think strategy analysis can happen without logic. I wanted to show you some of the mathematical logic that goes behind winning games this morning. This application is much more widespread. It's used in so many places. And frankly, the logic games, I don't think they can exist without strategy. So I don't think they're not like a separate thing. Play them all, man. Any other questions? Okay, thank you for inviting me. Have a good day.